So in last lecture we looked at functionals and derivatives of functionals, functional derivatives. This lecture we're going to introduce functional integrals, discuss them briefly, and then look at the beginnings of Ginzburg-Landau theory. So we've seen what a functional is, and a functional is something which takes a function here, phi, and the functional j maps it onto one number. Say this number here, you can define it in terms of integral, but it takes a function phi and maps that onto a number. And that's what the functional j does. Okay, now some functionals are defined in terms of integrals, path integrals, integrals over some quantity over a path. So here's a typical one here. Okay, that's a functional. That's an example. Now, we've seen previously how to get functional derivatives of functionals, and the derivative of a functional turned out to be a function. Okay. What about functional integration? Okay. Now, we're going to discuss functional integration briefly. We're not going to do any functional integrals, normally because they're impossible to do, but I'm at least going to show you what they mean. And we need to do this because a little bit of the theory for this subject is written in terms of functional integrals. And if you don't know what functional integral means, we're going to be in trouble. Okay, so when you see a functional integral, the typical example will be the partition function. Here's a partition function, and this is a functional integral. So z is the partition function, here's a functional integral. So you've got this funny symbol, big D phi, and you've got the Boltzmann factor there. Okay, so that bit's familiar. This bit is a little less familiar. Okay, so phi x is our field. E of phi is the energy functional. In fact, it's the free energy functional. And integral d phi means functional integral. I'm going to define what that means in a minute. Okay, so let's do this now. Okay, function integrals 2. So let's go back to ordinary integrals. So an ordinary integral like this, in the calculus you've known since high school, what that means, of course, is you take your y-axis and your x-axis and your function y equals f of x, and you divide the whole system into a series of boxes, and then you have those boxes of width dx, and you basically sum up the areas of these boxes, and as dx goes to 0, you hope that that reaches a limit. And so you just do this sum, and the limit of that sum is the integral. Okay, that's ordinary calculus of functions and integral of a function. Okay, we're going to try and do functional integrals, which is a different thing. Okay, and we have this symbol, big D phi, with an integral sign at the front. What we mean when we do that is an infinite nest of multiple integrals, minus infinity to infinity, d phi 1, d phi 2, d phi 3, up to infinity of these. Okay, where we have some function phi x, and we've discretized phi x. So what we've done, if we go over to the next slide, is we've taken phi x and evaluated at certain fixed points, x1, x2, x3, x4, everything up forever. And each 5x1 we've called phi 1, and 5x2 we've called phi 2. So phi 1 is the value of phi at x equals x1. Okay, so that's what we've done here. And then what we do is we integrate over all possible values of phi at x1. So suppose that was x1 just there. We integrate over all possible values, so in other words from minus infinity to infinity, of that number. And then we do the same thing for phi 2 here, etc., etc., etc. So we end up with a whole lot of integrals of this function. So in other words, what we're doing when we're doing d phi 1, d phi 2, d phi 3 here is effectively we're taking every single possible function, not just this one, but one looks like this, okay, one looks like this, every single possible one, and its value at x1, x2, at x3, at x4 in our discrete system can take any value. We're doing that integral, that sum over every single one of them. Okay, so that's what that symbol here means. And in ordinary integration of a function, we just sum phi I times the box width. Okay, that's this thing here. Okay. In functional integration, we vary the value of phi I over all possible values and do this for every possible phi I. And of course here I've discretized it, phi x1, phi x2, phi x3. But of course to do a proper functional integral, you have to do this in a limit where these x1s, x2s, etc. cover the whole real axis. So you infinitely discretize it. Okay? Not into 10 pieces, but into an infinite number of pieces. And do that integral. Okay? And in the continuum limit, we get the functional integral d phi of something. So we have to put out what we're doing the functional integral of. That's not the functional integral, that's the dx part. The dx part is this. Okay? So that's what a functional integral means. Okay? So, we'll give us some examples in a minute. All right. So, the terrible thing about functional integrals, as you can probably imagine, almost no functional integrals can be exhibited in closed form. So, for instance, you can differentiate most ordinary functions, or ordinary functions you differentiate. Integrating things for ordinary functions, well, some of the time you can do it, and some of the time it's not possible. A lot of the time it's not possible. For functional integrals, almost nothing is possible. You can write down a formal result, but you can't actually evaluate that result. Most functional integrals you find, if you make one up, they'll diverge. They go off to infinity, as you can probably imagine, given the way this thing is constructed to go off to infinity. You can imagine meaning to actually do, given an example of infinity. However, ratios of functional integrals can give finite results, and often we're interested in ratios of the two, so you get finite results. Most integrals in practice, when you do them, and we're not going to be doing any of them, so don't worry too much, but most of them, when you actually do them, are done by perturbing about known functional integrals, usually Gaussian ones. Okay, so we will not be using them in our calculations, but they'll appear in the formalism, so that's why I've told you what they are, what they look like. Okay. So, let's get on now to the application. And this particular part of the course was invented by two of the giants of theoretical physics in the 20th century, Mr. Ginzburg and Mr. Landau, both of them Jews from the former Soviet Union. When I say Jews, they're secular Jews. But you'll find that them and their compatriots contributed enormous amounts to physics in the 20th century. Ginzburg only died, he died sometime during this century, and Landau unfortunately died in the 1960s after suffering a terrible car accident. But very few people have contributed as much as these two to theoretical physics. So, Ginzburg-Landau theory. What is it? And it's described in terms of a field or order parameter phi of x. Okay, so we assume the state of the system is specified by phi of x. We replace all the microscopic details by the fields phi of x of the order parameter. So we've discussed this before. We take a magnet and we get rid of all the spin directions and use an average field over a small volume. So we take some, like it might be 150 spins here, and we average the magnetization, for instance, over that volume, and that gives us the order parameter. So instead of having spins S1, S2, S3, S4 up to S Avogadro's number, we just have the magnetization MR, which is a continuous smooth field. Okay, that's what it is. Okay, it's a continuous smooth field, and we don't have all these individual little spins, which is what you have in reality. We have this continuous smooth field. All right. So similarly, if we had a two-particle fluid, we could describe the system by all the positions of all the particles. Okay, but what we do is we describe it not by that, but by the density difference of greens and yellows in a region. Okay. Now, that sounds a little bit weird, possibly, but in fact, we already do this all the time in physics. For instance, in electromagnetism, if you have a sample of silicon, the electric field is varying crazily in that sample. If you here's a nucleus, okay, we've got protons and neutrons and other things. You've got electrons out here, okay, and if you happen to get too close to one of the protons, the electric field goes sky high. Okay, similarly, to do close to one of the electrons, because electrons are moving about in a cloud, so maybe getting close to one is a tricky concept. But if you know that if you get close to the nucleus in silicon, electric field is wildly positive, for example. Okay, so but when you're actually using, say, calculation in undergraduate years, you replace these by these very smooth fields, E, P, and D, and you don't worry about the fact that things are exploding near a proton. Everything's smoothed out, and that's more or less what we're doing here. Okay, the idea of ignoring the rapid variations that occur on the very small length scales and trying to make things a bit more mesoscopic. Okay. So, what are we going to do here? We're going to introduce what's called the Landau free energy, or sometimes a Landau-Ginzburg free energy, which is E of phi. It's called a free energy, and we'll go into that in a minute. Okay. A function 5x specifies the state of our system. If we know 5x, we know what it looks like on a small, but not atomic scale. Okay. And E of phi is a functional of phi. So that's why we're doing functional integrals, functional calculus. And we can make many copies of the system and bring each one to thermal equilibrium. Okay, so let's make many copies, bring them all to thermal equilibrium. Just as a gas has many states compatible with thermal equilibrium, so if I take a gas in a box, one state might be this one, another state might be this one. Okay, they're all compatible with thermal equilibrium. There are many phi x's for any temperature, so there could be many field representations for any given temperature at equilibrium. And we don't make many copies and we get an ensemble. Okay, each different field variation across a sample will give us in general a different free energy. Okay, and remember, this thing takes the field phi, which is a function of three-dimensional space with many number of variables, and matches it to one number. So one number, okay, gives us the free energy. Right. So let's do a really simple example of this. We take the Landau free energy functional in a system of length L to be this. So we're going to have one-dimensional system. We're going to write it like this. Okay, that's our Landau free energy functional. We're going to posit that as our functional, and it's a square gradient, which you've seen before. Okay, this would be a good model for the stretching of a chain of atoms. So suppose we have a 1D chain of atoms, and we're just trying to displace them. They have some natural equilibrium position, which is this separation here. And let 5x be the displacement. So how much each one is displaced. Okay. Now 5x is a constant. In other words, this one's displaced by 1 angstrom, this one's displaced by 1 angstrom, this one's displaced by 1 angstrom, etc. Then of course the energy of that system doesn't change. All you've done is displace the atoms to this way equally. And of course if 5x is a constant, then divide x is 0 and the energy functional would be 0. Okay, so that makes sense. However, if I did a so-called piles distortion where I took, say, 2 of these and compressed them, another 2 here and compressed them, then 5x here, 5x would be positive, here it would be negative, here it would be positive again, here it would be negative, and dividing x would certainly here would not be 0, and I would get some square gradient free energy. And that's basically, if you did that, this would be a very good approximation to what the free energy should be, at least within a constant. You might have a constant out the front here, but that's the answer. Okay, so let's do the Landau. That's an example. Now we can take this example a bit further. Let's not consider all possible phis, but let's just take some phis of this form, where I make a sinusoidal displacements. Sinusoidal displacements, except in one dimension. So I'm moving some of these a lot, and some of them not very much, and some of them only a little bit. Okay. I'm going to take a sinusoidal displacement, A times sine 2 pi nx divided by L, where n is some number and A is the amplitude. Okay, I can plug that into our free energy here, my free energy functional here, and get an answer. It's pretty easy. Just do the integral, and I get this answer. Okay, rapid variations in space, large n, so we're doing this, of course, they suffer a significant free energy penalty. Large amplitudes suffer a significant free energy penalty as well. Okay. Now, when you're doing statistical mechanics, of course, you don't do this. In a real statistical mechanical ensemble, we won't be looking at 5x's which have this special form, but all functions 5x. So not these ones, but absolutely everything. So up here we're looking at very simple ones, look like this, very repetitive. But in reality, when we do a functional integral, we don't just look at that or any variations of that. We look at everything. We look at things that look like this and things that look like that, and any sort of variation you like, okay? Because we have to sum over all possible 5x. That idea takes a little bit of getting used to, but you're used to it already when calculating partition functions. You sum over all states, and here we're summing over all possible fields. Okay. So what do we do in our situation? Well, we're going to have to, of course, use the Boltzmann factor here. And to make a statistical ensemble, we take a set phi x of fields and weight them by this Boltzmann factor. Remember, this Boltzmann factor now makes perfect sense because remember, you give me a phi, I give you a number, e of phi. So this is just x of minus beta times a number. Okay. Now, you might expect this to be called the energy rather than the free energy, but we'll explain again soon why that's not the case. Okay. So the partition function then is just defined to be that. Okay, you now at least partly understand what a functional integral here means, and there's a Boltzmann factor, and so you're doing the functional integral of the Boltzmann factor over all fields you can possibly imagine, so that's the answer. Okay, those fields which have a low E phi, in other words, E phi, for instance, is negative, very negative, for instance, are much more strongly represented because this factor here gets big. Okay, so you can imagine fields that have very high E are not represented much, and fields that have very low E tend to be more strongly represented, at least at finite temperatures. Okay, just as they would be for ordinary spin systems or discrete systems. Okay. All right, and we'll stop there, and next lecture we'll go on and look at specifically the kind of expressions for the Ginzburg-Landau free energy which Mr. Ginzburg